Good afternoon, everybody. Any questions on the lab last week or any general module questions? Anything pressing? Okay. This week is the last Abacus lab, so pretty short and sweet. Some of you have already started it, that's fine. And then next week, there's no lab next week. So there is one this Thursday, but there'll be a gap week next week, which is week 4. I'll send an announcement reminder because it's in your timetable. Today, I'm going to talk a little bit about accuracy and order of accuracy. So we mentioned this last week when we talked about discretization error. So I'll give you some more concrete feeling for understanding what is accuracy and order of accuracy. So I'll do some numerical calculations and show you what I mean by accuracy and what I mean by order of accuracy. And then maybe at the end of this lecture, if I have time, then I'll start on triangular elements. Consider this function, this 1D function. So y, the vertical axis, is a cubic polynomial. So varies this function of cubic lengths. And my question is, well, what is the slope at this value? So this is an actual polynomial. You can plug it in, these numbers actually make sense. So if we had the actual function, then you just differentiate it and you get slope. That's fine. But in general, we don't know what this function is. We just know values at particular places in space, and we might call those nodes. So in a finite element mesh, we might know the value of the space at particular points, but we don't know the general description of the function. So okay, we use this piecewise polynomial approach, and that's how we approximate it. And so what does that do in terms of accuracy or order of accuracy? So let's imagine I have a point B and a point C that are equidistant from point A. And these are the coordinates here, so this is a minus 0.5, but it doesn't matter. And then imagine if I were to approximate the slope using closer points. So let's do both of those calculations. So if I had the further away points and the closer points, and what happens to the error? So first, let's talk about the accuracy. So not order of accuracy, just the accuracy. So I guess you guys can differentiate. So if you differentiate this with respect to x, you will get this quadratic function. So that's the definition of the slope at every point along this curve. And if you sub in the coordinates for A, the x coordinate is 0.5. So if you sub that in here, 0.5, you'll find that the slope at this point is minus 4.25. So minus going down, 4.25 is the rate at which it's going down. So the actual correct slope at A is minus 4.25. But now let's do it numerically using difference. See how accurate our approximation is. So we'll use point B and point C. So if we just use 2 points and we use this central differencing or this linear approximation, we can say, well, the value here minus the value here divided by the distance, that's an approximation of this. It's not equal to the slope, it's an approximation of the slope. And that's essentially what we're doing with a finite element. We're approximating the slopes at each point. So sub in the values here for this minus 1.65 and the y value there divided by the difference in x. So you can see it's minus 3.25. So the correct answer is minus 4.25, but this approximation is minus 3.25. So the true slope you can see is steeper, minus 4.25, than our approximation, which is a little bit less. So what we mean by the error is just the difference between our approximation and the actual value, the real value. So if I get the difference in 4.25 minus 3.25, the difference is 1. So I'm taking the absolute value here, but errors can be signed or unsigned. You may or may not take the absolute value. So the error here is 1 in our approximation. So the accuracy of a numerical method is defined just by the magnitude of the error. It's just the error. So a method that's more accurate just has a smaller error by definition. The order of accuracy is a different thing. It's not about the magnitude of the error. So what happens if we choose points that are closer to A? So instead of B and C, we choose B prime and C prime. So in this case, I have half distance. So the distance here has been half, the distance there is half. And the distance between B prime and C prime is half that of B and C. So if I do a linear approximation here, this minus this, you'll see 1 minus 0 divided by 1, so that's minus 4. So the true slope is minus 4.25. That means our error is the difference between 4.25 and 4, so it's 0.25. So it's a much smaller error. So even if you look at the green line here, which is faint, that's under predicting the slope, you can see the pink line here is actually pretty close to the slope. Like it's much, much closer to the slope. But still there's an error of 0.25. So if we use points B and C, we got an error of 1. And when we halve the spacing, using this linear approximation, we got an error of 0.25. So the error, even though we halved the spacing, the error didn't halve, the error became 4 times smaller. So if the error halved, it will be a so-called linear method or a first order method. But if it's 4 times smaller, so it's 2 to the power of it, then it's the second order method. So using this linear approximation gives us the second order of accuracy method. So the order of accuracy is referring to the rate at which the error reduces as you reduce the spacing. So it doesn't matter if the error is very large. It's just how the ratio of errors as you reduce the spacing. So you could potentially have a method that has a higher order of accuracy, but the errors could still be large for a given grid. So generally, if the mesh refinement ratio is OR, so in this case, if I'm halving, I mean OR is 2. So the ratio of the large spacing to the small spacing, that's what my OR is. So in this case, I've selected it to be 2, just to make it easy. But if you have a certain mesh refinement ratio or ratio of these points, and the order of accuracy of your method is P, then the error reduces at 1 over OR to the P. So for example, if OR was 2, that means you're halving the spacing each time. And if you had a first order method, it will be 2 to the power 1. So that means that the error would just halve each time you halve the spacing. So a first order method, the error halves every time you halve the spacing. Whereas a second order method will be 1/4, a third order method 1/8, 1/16, etc., etc. So that's what we mean by the order of accuracy as opposed to the accuracy. So there's theoretical order of accuracies with finite element and finite volume methods, but at times we may not observe the actual theoretical order of accuracy. We may observe something that's a bit lower. So imagine we have our points B and C and B prime and C prime. So if I were to move the positions of B and C, but still keep them outside these B prime and C prime, or move the positions B prime and C prime, but still keep them inside. So I still have a coarser mesh, which is green, and a finer mesh, which is pink. And are there cases where I won't see the theoretical order of accuracy? So with this linear assumption, I said, well, it's second order accurate. We should expect the error to be 4 times smaller as long as we have the spacing. And so are there ways that we could move this or choose these points that may violate that? So there are a few. So one, if B and C and B prime and C prime are not equidistant from A, then the order of accuracy will reduce by, well, towards 1 order of accuracy. So in this case, it would reduce towards first. So to put it a different way, if my point B was very close to A and C I moved over here, and then my B prime was also close to A, but C prime was halved. So I'm still halving the spacing, but I'm trying to calculate the slope very close to one edge, then that will start to approach first order. So it's only when they're equidistant that you actually get this order of accuracy. What does that mean for finite element mesh? Well, uniform smooth meshes tend to give you closer to the theoretical order of accuracy. So if you have very large elements and then going to very small ones very quickly, or very poorly shaped elements, it tends to reduce the order of accuracy of your method. For more elaborate functions, if you're far from the so-called asymptotic region, and we talked about this asymptotic region last week. So if you imagine that the green points were really far away and there's lots of more oscillations, then having the spacing, the error may reduce, it may not reduce because you've got bumps. So possibly the coarser mesh could give you a more accurate approximation, just because you're very far from the where the curve is close to point A. So in this case, the asymptotic region is when you're starting to get over these bumps and you're into this region that starts to be more straight, then that's where you'll see the artifacts. So away from that, it doesn't really go. Another case, if you've a discontinuous slope, so if the true value of the solution has a discontinuity, or maybe its slope has a discontinuity, then this type of order of accuracy you may not expect. So what does that mean in practice? Well, maybe for fluid mechanics, if you've shock waves in your solution and you around the shock wave, the method may lose order of accuracy, or you may need some sort of special method to accommodate that. So are higher order methods always more accurate than lower order? Generally, higher order, somewhat vague term, but it mostly means greater than second order accurate in literature. So typically having a higher order method is better, but just because you have a solution using a higher order method and one with a lower order method, that doesn't mean the higher order method is more accurate, because the order of accuracy doesn't refer to the error, it refers to the rate at which the error reduces. So a simple example would be, imagine I have a quadratic fit, so I have B prime prime and C prime prime. I need 3 points to fit a quadratic, so I'll use the value of point A as well. So I'll fit a slope here, or I'll fit a quadratic curve here, and use that to calculate slope. So you'll see the slope here is pretty close to 0, or a little bit less than 0. So if I'm using a large spacing with this quadratic grid, in this case, the error is much worse than a linear fit. So maybe if your spacing is larger with a higher order method, the error will be worse than if you're using a finer grid with a linear method. But it depends. So in this case, if I use the same spacing and I fit with quadratic, you would get a smaller error. But you can't just say for example, in finite elements, you cannot generally just say the quadratic elements are more accurate. It depends on the mesh density, but also maybe on characteristics of the solution. So that's relatively short and sweet. Any questions on that? It's just something that I notice people get confused by, order of accuracy and accuracy. So that was the purpose of those slides. Okay, now I'm going to start on the third set of this introduction to the finite element. So in the lectures last week, I talked about the finite element method, where we use a physical approach to derive out the stiffness matrix, or the governing equations for finite elements. And we took a 1D truss element, and we followed these 6 steps, where we assume the functional form, wrote that in terms of the nodal displacements, calculate strain, stress, and then we use this principle of minimal potential energy to get our equilibrium equations, which is our stiffness. So I'm now going to just show how that applies to 2D triangular structural elements. And I'm going to stop here. I mean, you can do the same thing and go to 3D elements that are, say, brick elements, like things that look like cubes or cuboids. So 6 faces. You can do the same thing, but they just have so many unknowns that the equations become very tedious. And it's exact same approach. So imagine we have a 2D triangular element. You're going to assume Cartesian XY axis. How is the triangle defined? Well, it has 3 points joined by straight lines. So I'm going to say points 1, 2, and 3. It doesn't matter the order. I'm just assuming particular order. X1, Y1, X2, Y2, X3. Where are the coordinates of my triangle? And this is a structural problem. I'm going to limit it to elasticity, but you can see how it can be generalized to more exotic material models. So for linear elasticity, we have a Young's modulus, like we did for our truss element, but because it's a 2D element now, And we also have this Poisson's ratio effect. So if you take most materials and you pull them, they tend to contract in the other direction or do something in the other direction. Whereas the truss element didn't really have a second direction. So we have Poisson's ratio, and then we have a thickness as well. Even though it's 2D, we can actually represent different thicknesses in the third direction. So we'll have split up our geometry of interest into these triangles. And we're going to try to calculate the displacement at the 3 nodes for each element, or for all the nodes in our mesh. So displacement here is a vector as well. So at each one of these nodes, you'll have U1, so U1, V1, U2, V2, U3, V3. So U being the X component of displacement, V being the Y component of displacement. So you can have a little displacement vector at each point. So unlike our truss example, in the truss example, we just had one displacement, which was the axial displacement. It's just a scalar. And we just had one coordinate, which was, we call it XL, which is the coordinate in the direction of the truss. But for these triangular elements, which are 2D structural elements, we have 2 coordinates for each node, and we have 2 unknowns, 2 scalar unknowns, or 1 vector unknown. So six numbers are unknown for this element. So following this kind of direct finite element derivation approach, we'll follow these 6 steps. We're going to assume the functional form of the displacement field within the element, express that field in terms of the nodal displacements, introduce the strain displacement relationship to get the strain, introduce the constitutive law to get the stress from the strain, and then write the equilibrium equations for the element to get the relationship between nodal displacements and nodal displacements. So I'm going to use this general approach, and all structural elements can be derived in this general way. But just to repeat, there are different approaches to deriving finite element equilibrium equations and stiffness matrices in literature, and they'll all give you the same stiffness matrix, but some of them maybe are like different kind of mathematical philosophical approaches to the work. So following the approach we did in the truss, let's assume or approximate the displacement within this element using the simplest polynomials. So just these first order polynomials. So we have 2 fields here. We have the U field and the V field. So U is the X displacement. So imagine the X displacement will vary in some way from across the element between the nodes. So the true displacement field, we don't know what it is, but we're going to use this approach of approximating it with a simple polynomial within each element, have lots of elements, and then as we refine the elements, then this discretization error will reduce at a certain rate dictated by the order of accuracy. So let's take a simple polynomial. We'll say that U is a function of X and Y in the element, and we'll define some constants, alpha 1 plus alpha 2 times X plus alpha 3 times Y. So before, for the truss element, we just had alpha 1 and alpha 2. It was by X and we know Y, but now it's 2D, so we have a Y component. And then V, the vertical displacement or Y displacement, well, that can vary differently. That's independent of U. You can have different X displacements than Y displacements. So that will have its own constants as well. So we have six constants to describe how the displacement varies. So if this is a first order polynomial, these are called linear shape functions or linear interpolation functions. These are the default in Abacus. But we could use quadratic ones. So we could, with extra constants, have an X squared plus a Y squared, and actually an XY term as well. So 3 extra per each one. And that would give us quadratic functional forms or quadratic shape functions. So in Abacus, you go to the shape, the element controls, you can tick on quadratic if you want it as well. So you'll say, well, how can I calculate the constants if I have quadratic? How can you fit a quadratic curve with just 3 nodes? Well, in that case, if you select that, Abacus actually adds extra nodes at the mid sides or in the center of the element. There's a few different ways to do it. You may just put them on the outside, you may put some on the inside. There's various ways to do that. And that's where Abacus stops. You can't go to cubic, but other finite element methods out there or softwares out there might have cubic or fourth order, etc., etc. Okay, so step 2. So once we have this functional form, how do we calculate these alphas? So for each node, we know its XY coordinates. That's a known thing. And then we know that the value of that node must be given by U1, V1 at node 1. The value at X2, Y2 must be U2 and V2. So we have 6 values and 6 unknowns, so we can sub that in. So at node 1, if we sub in X1 and Y1 into the U equation, that will give back the value of U1 by definition, and the same for V1. So then you'll get 6 simultaneous equations in terms of these alphas. So this is, you can see, is probably pretty tedious. I've asked you to do this, it'd be tedious to just to solve these. But I've done it for you and other people have done it already. But this is why you can see if we go to 3D elements that are bricks, quadratic elements, it would be very tedious. So after doing that and subbing everything in, you'll find that the X displacement varies as a function of X and Y in the triangle. As a function of these 3 terms. So notice we have X here, Y there. And then what are all of these things? Well, A is just the area of the triangle. And then U1, U2, and U3, they're the displacements at the nodes. Because remember, we're trying to express it in terms of displacements at the nodes. And then these A1s, A2s, and A3s, and B1s, and B2s, and B3s, and Cs, these are just geometric quantities. They are, I'll give you the formulas for them, but they're essentially like widths in the X direction and widths in the Y direction of the triangle, lengths of the slides. So it's basically just giving the displacement field everywhere in the triangle as a function of the shape of the triangle, the coordinates of the triangle, and the displacements at the nodes. So if you know the displacements at the nodes, then you can define what the displacement at any point in the triangle is, or at the nodes. And if you wanted to check this works okay, if you were to sub in, for example, X1, Y1, then this should give you back U1 for the U equation and V1 for the V equation, so that the you can check that these do actually make sense. So A is the area of a triangle, and you can do the area of a triangle as half the base by height, but in general, you can do it in terms of this cross product as well. And this is what the A1, the A's, B's, and C's are. So they're just functions of the coordinates of the nodes. So for example, like Y3 minus Y1, it's kind of like a height of the triangle in a particular direction. So these are all kind of measurements of the height or width of the triangle in some way. So if you picked a very simple triangle that lines up by one, you'll see a lot of these reduced down to just heights and widths. So they're known geometric quantities. Okay, so now we have this particular functional form. What does that mean? So imagine that I put the triangle laying down, and then I introduce another axis, a height, and the height above the plane just represents a value of U, just as a way to physically interpret it. So imagine that we knew the value of U1 here, then it's a small value, we'll just represent that as a small height. We know the value of U3, it's a larger value, we represent like that, and the value of U2 is even larger. So what this equation here is just defining an actual plane. Or a different way to think about it, it's defining like an interpolation. So if I wanted to know the value of U anywhere in this triangle, I just look at the height of that plane above that coordinate. So for example, if I go down to this node here, right at this node is just equal to U1, right at this node is equal to U2, right at this node is equal to U3. Right in the very centroid of this element, it'll actually just be the average of all 3 of them. If I go at the halfway point between U1 and U2, it'll be the average of U1 and U2. If I go at the center of any of the edges, it's the average. And then anywhere in between is just a generalization of that. It's just a way to interpolate between the 3 values, and it's fitting it as a linear plane. So that's all this function is. It's just a way to interpolate between the 3 nodes. If we did have quadratic elements, there would be extra nodes there, and then this surface would be curved. So U varies like that, and V also varies in a different way. It'll just have different heights, but it's still a flat plane. So that was step 1. Step 2, we assume the function form, in this case a linear or a first order polynomial. We then sub that in to get the function form in terms of displacements at the nodes. So step 3 is the strain displacement relations. So in the 1D truss, the strain is just defined as, well, delta L over L. But we said, well, we can generalize that and say that's just the gradient of the displacement. So it's du dx, or delta u delta x. So that's just the change in length over it. But the more general expression in 3D is that you have this gradient of u, so it's a du dx, where u here in bold is the vector u, so it's u and u. And then we take the symmetric component of that. So what does that mean? Okay, let me write it out. So the symmetric component just means half that tensor plus the transpose of it. So if we write this out in component form in 2D, it just says that the strain, which is a tensor, and this is 2D, so it has an xx component, xy, yx, and yy. Strain by definition is symmetric, so these two will equal each other. So if you look at the xx component of strain, it will be du dx. So it's how u is varying in the x direction. So if that was a simple 1D element, it's like the delta L of the triangle over the length in the x direction, whereas this is the delta V of the triangle in the y direction overall. And then the shears are defined. So since we now have a definition of displacement in our element up here as a function of x and y and constants, so the nodal displacements are they're just defined at the node, they don't vary in space. And A's and B's and C's and the capital A are just geometric quantities, they're just like widths, heights, etc., thicknesses. They're all constants. Then we can calculate each one of these. So for example, if I want to calculate du dx, then I can just differentiate. So if I du dx, I'll check the first term, it doesn't have an x. The second term has an x, so differentiating it, just that goes to 1, so you're just left with that thing. And then the third term just is a y, so that's not a function of x. So you can see that this thing here just represents the strain in the intersection. So du dx, we can calculate this. It's a function of the displacement, u1, u2, and u3 at the 3 nodes, divided by the area, multiplied by these geometric weights. Oftentimes in finite element nomenclature, you will use row vectors and column vectors just to make it easier to program the method, but also to write out the equations. So if you check here, we have b1, b2, b3, and they're multiplied by u1, u2, and u3. So we could define this b row vector and this displacement column vector. So if you multiply row by column, you'll see it's b1 by u1, b2 by u2, b3 by u3, all divided by 1/2n. So you get back this scalar, row by column, so it's a 6 by 6. So why do we do that? Well, it just lets us come up with a common nomenclature for describing the strain components. So if that's the xx component, we can do the same thing to get xy, so we can see x, y, which is equal to yx, is differentiating u respect to y and v respect to x. And so you can write it out in this kind of shorthand notation of a row vector that looks like this, like the same column vector, the same for the y line. So the column vector here, u1, v1, u2, v2, u3, v3, that represents the 6 scalar unknowns in the element. So it's the displacement of each of the 3 nodes within the element. So it's the vector of unknown displacements within the element. So a couple of things to point out about this linear triangle element. X and Y doesn't appear anywhere in the strings. So after we differentiated, the x's and y's disappeared. So this tensor here, or this row vector here, here, and here, they have no x and y. So they're not a function of x and y, x and y. So these C's, B's, A's, they're just like widths and heights. They're not a function of x and y. So that means that strain is constant within the element. So within these linear finite elements, these linear triangles, the strain is actually constant. So the displacement is varying linearly, but the strain is constant. So it's the same value here, as here, as here, as here, as here. So that's obviously not true in reality, and that's as a result of our approximation. A different way of thinking about that, if we thought about that plane that we fit through the displacements, the strain is basically the slope of that displacement plane. So that slope of that plane is constant. It's that means the strain is constant. If that was a curve, then the slope is varying, that means the strain is varying. So if your plane is flat for the displacements, then the gradient of it has to be constant. A convenient thing then of writing it in this shorthand is I can just bunch those three rows together. So I can get a 6 by 3. So row by column will give you the XX. The middle row by the column gives you YY. The last row by the column gives you ZZ. So this is called void notation as well. So if I can write it out like this, by the 6 unknowns with this geometric matrix to give strain. The reason we do that, as we'll see later in these slides, is this general format can be followed for much more complex elements. So elements that are quadratic or more complicated in shape, like prisms or something like that, pyramids, will always be able to create this matrix and just multiply it out. So it makes it easier to compare different elements and code them as well. So using this notation here, so I'm using these squiggles to represent a column, and then I can't remember what I used to represent a row, a slightly different symbol. So you can say the strain in the element, which is constant in this case, is XX, YY, and XY. That strain is equal to this matrix by 1 over 2a. So this matrix by the 1 over 2a, and I'm going to just call this the B matrix. And then this column vector here, delta, represents the unknown nodal displacements. So for all structural elements, no matter how complex or what functional form they use, we can write this same format using this B matrix. Okay, so we functional form, wrote in terms of the nodal displacements, and we introduced the strain from the displacements. So 2 steps left, calculate stress. How can we calculate stress in terms of nodal displacements? And then we can get to equilibrium equations. So we're going to use the constitutive law to calculate the stress. So generally, the stress is just equal to something, some set of material properties by the strain. So following the same kind of void notation, we can introduce this C matrix, and it's called a constitutive stiffness matrix, or sometimes people call it a material tangent. There's various different names. Material matrix. So for in 2D, assuming linear elasticity, it will look like this. So there's lots of ways we can write this stress equals strain in 3D. We can write it in Einstein or index notation or in tensor notation. But for our finite element approach here, this is the most convenient. So what does this say? It says that let's say XX stress is equal to rho by column. So let's first imagine the Poisson's ratio is 0, because this has a direct analogy with 1D, which we've already done. So let's imagine this mu here is 0. So then if mu is 0, if your Poisson's ratio is 0, then it says the stress in the X direction is rho by column. So it'll be 1, 0, 0. So it'll be just 1 times this. So it says the stress in X direction is equal to the strain in X direction multiplied by Young's modulus divided by 1. Because if that was 0. So it's actually just saying stress in the X direction is equal to Young's modulus by the strain in the X direction. And the same for the YY. If Poisson's ratio is 0, then the stress in the y direction is equal to the Young's modulus by 0, 1, 0. So that row by that column is just 1 times the strain in the y. So you can see if your Poisson's ratio is 0, it's basically just like you've 1D material behavior in the X direction, 1D in the Y direction, and 1D in the shear. But when Poisson's ratio is not 0, so for example, for steels or other engineering alloys, it might be, let's say, around 0.3. So in that case, the stress is equal to E divided by 1 minus 0.3 squared. So that's a number less than 1. So that makes it apparently higher. So because of Poisson's ratio, it seems kind of stiffer in the direction you're pulling. And then it'll be 1 by your strain XX direction. We had that before, but now we also have a mu in the YY direction. So it means that even if the strain in the XX direction is 0, you will still get a stress in the XX direction if the YY strain is non-zero. So if I'm holding something in a constant length, and someone else is pushing or pulling in the perpendicular direction, that will generate stress in the direction I'm pulling it. So that's this 3D effect, this +1 effect. Okay. Once again, the stress is just some constants, some material properties by the strain. So those constants, Young's modulus, they're not varying in space. Although they could be, you could have a Young's modulus varying in space. But here we're assuming it's not. So if it's not, then that means stress is not varying in space. So within the element, if the strain is constant, then the stress must be constant if the E's and U's are constant. So if you're not function of X. So that means for a linear triangle, the strains and stresses are. And these formulas, we already have those formulas. So once you calculate that, we can just plug it on. You get the stress. Okay, so then the last step to get our stiffness matrix for this triangle is we're going to use this principle of minimum potential energy to derive the element equilibrium equations. So if you remember when we did this for the spring, and we only had one scalar unknown, and the spring, one side was fixed, the other was not fixed, we said, well, if we apply a force, the spring will move, and we'll get a certain displacement. So if we know that displacement, if we were to perturb that displacement anyway, we would make it a little bit more positive or a little bit more negative. The total energy in our system will increase. So the equilibrium value of that displacement, the point at which it settles and stops moving, that's the point of minimum total potential energy. And our total potential energy we define as this internal minus this external value. So how do we calculate that? Well, then when we did it for a truss, we said, well, the energy, if you imagine you have a spring, it's just, is it half kx squared? But the generalization of that when you have stress and strain is, if you multiply the stress tensor by the strain tensor, this is a double dot product. So if you have two tensors, you multiply them together to get a scalar, because energy is a scalar always. And then you integrate that over the volume. So integrated over the volume just means add it up for all the material in the volume. So we can just plug in our definitions of stress and strain that we got in all the previous slides and then calculate this thing. So our stress was C by strain. That was our stress. And then multiplying again by strain, that means we have two strains in. So stress is C by strain, and then we're multiplying by strain again. So it's like strain squared by C. Take the analogy back to our spring, the definition of spring, the C, the material stiffness, is just like K. And the strain here is kind of like an X. So it's basically just like half kx squared. So it's the same as a spring. It reduces to what we did for calculating the area under the force displacement curve in the spring. It's just this is the generalization for 2D or 3D elements. So I think, yeah, these L kind of brackets mean it's a row, and these squiggles means it's column. And then this is a matrix. I've taken these outside the integral because strain is not a function of XY coordinates, and neither is C and neither is the other strain. If they were, you would have to leave them inside. So one thing I'm not going to go through so much in this course, but happens in practice, is this idea of Gaussian integration or Gaussian quadrature. So the idea there is if strain or C does vary within the element, then how do you calculate this integral? So the approach they will use in finite element methods is, well, just calculate the value of that integral at certain points, like the center of the element or a few locations within the element. And that lets you approximate that integral. So if it did vary in some higher order fashion, then if you just add the values at 4 points in the element and take some weighted sum of them. So that's this idea of so-called Gaussian integration or Gaussian quadrature. So I'm going to avoid that, but that's something that gets used. Okay, so this is just this here. This is basically integrating a constant 1 over the volume. Just by definition, that's the volume of the element. So the volume of our element is just its area multiplied by its thickness. Okay. And what did I do on this line here? Well, I basically just took the strains and I wrote them in terms of displacement. So if you remember, we said the strain is equal to the B matrix by the nodal displacements. So for each strain here, I'm writing the B matrix by the nodal displacement. And here. So the B by nodal displacements for that one, And then because this is a row 1 to be the nodal space, it's 5 to be transposed, just to make it work. So I'm just replacing this, writing this epsilon within the element in terms of the nodal spacements on this B tensor. So once again, these B's, remember, are just some geometric quantities. They're just measurements of heights and widths on areas, whereas the C is integer quantities. I move A and T just over the left-hand side as well. So you can see I have this nodal displacements here and here. I have these known geometric quantities, and then I have a nodal stiffness. So that was my definition of internal energy. And actually, this general expression works for any elements in 3D or any linear form, which is convenient. So this is the same, if you can understand this, this is the same thing that for any more complex finite element. So that's the internal energy, the internal potential energy. So the external, or the work from external forces potential energy, it's just the applied force by the displacement of each node, and then we just add them all up. So the vector force by the vector displacement of this node plus the vector force by the vector displacement here plus the vector force by the vector displacement. So we can write that as the 6 displacements multiplied by the 6 force components. So that means our total potential energy is the internal part minus the external part. And then we get our equilibrium equations on our stiffness matrix by differentiating this with respect to each unknown. So the unknowns here are the nodal displacement we're trying to calculate. There's 6 of them. So this has 6 scalars: U1, U2, V1, V2, VU, right, U1, V1, U2, V2, U3, V3. So if we differentiate this with respect to U1, that will give us one equation. If we do it with respect to U2, it gives another. U3 will give us another. V1, V2, V3. So I'm calling those delta 1, just delta 2 to represent the components of this displacement unknown vector. So they will all be equal to 0 at the equilibrium point. So I can write those 6 scalar equations like that. So how do I differentiate that? Well, we can write out all the components, but that's really tedious. So you can just accept that this is what it's equal to. So if you notice here, we basically have a delta by a delta, like a delta squared. And so if we're differentiating with respect to delta, and that delta squared becomes just a delta, 1 delta. So we end with just 1 delta. And then essentially, it's kind of like x squared becomes 2x after you differentiate it. So that's where the half drops in. So conceptually, if that's what we did, you'd have to write out all the components to actually check that this makes sense. But the f delta here, you can see the delta drops. The delta squared or half delta squared just becomes a delta on its own. And then we're left with B, C, D. So this is a general definition of our stiffness matrix. So this thing here is our stiffness matrix by our unknown nodal displacements and minus the applied external forces. So this general form is the form used for all elements. So maybe if it wasn't 2D, this area by thickness, that will just be represented by the volume. So if you have an actual brick element, it'll be just the volume. But this general form with the B matrices and the C matrix, this is the general form adopted for all finite elements. And we could go back and look at the truss element and rewrite it in terms of this form. I want to see if it still makes sense. So then that's nice. We can represent our classic finite element form where I have our K delta equals F. Okay, so what does this thing look like? So even though it's a simple 2D triangular element, it's pretty tedious given the formula, but I think I've written it out here. Yeah, so you obviously don't have to remember these. But the way it's derived is actually not that complicated. It's just multiplying that B by C by B. It's just you have, is it a 3 by 6 by 6 by 6, 3 by 3 by 3 by 6. So you get something that looks like this. The things to note, if you go back to one of the first lectures, was this stiffness matrix. Once again, it's symmetric. It's the same in the upper corner as the lower corner. It's square. It has the same number of rows and columns. And in this case, it's just a function of material properties, E and U, and geometric quantities, the thickness, the area, and then these B's and C's are coordinates, are widths and heights and thicknesses. There's a lambda here as well. That's just another material property that's just a function of E and U. So this is called a second Lemay parameter, and it's just a function of E and U. It's just easier to introduce that, otherwise you get a more complicated form here in terms of E and U. So that's demonstrating how to do it for triangular elements. As I said, I'm not going to go to more complicated structural elements. You can find them in a book, and I can recommend books if you do want to know them. But they'll just follow the exact same approach. It's just the final form will be a little bit more tedious. So understanding those fundamental steps means you can understand how it's derived in general. Thanks very much. See you on Wednesday.